Welcome to the Explainer. Today, we're diving into a seriously high-stakes engineering concept. It's something that operates entirely behind the scenes of our modern world, yet, our very lives depend on it every single day. We're talking about how engineers pull off the seemingly impossible task of guaranteeing that a massively complex system, like, say, a metropolitan railway or an automated control network, absolutely will not fail catastrophically. I mean, how do you actually promise perfection in a fundamentally imperfect world?
Here's our roadmap for today. We'll start by defining safety assurance, then move into the HazID workshop, calculating system risks, the absolute need for independence, and finally, building the safety case.
So, here's the million-dollar question. How do we prove a complex system is actually safe? It might surprise you, but the answer requires a total shift in mindset. Engineers don't just build a system, flip the switch, and assume it's going to work safely. No way. In the world of high-integrity engineering, a system is literally treated as guilty of being unsafe until it is rigorously, meticulously proven otherwise. It's a proactive, relentless hunt for failure.
Okay, let's dive right into this. The formal industry term for this whole process is safety assurance. It's defined as the continuous evaluation of risk throughout the lifecycle to ensure the system meets specified safety targets. Now, the absolute keywords to remember here is continuous. This is not some single rubber stamp of approval you get at the very end of a project. It is an ongoing, relentless process that kicks off the exact second a system is conceived and doesn't wrap up until that system is safely decommissioned years later.
Step 2 on our agenda, the HazID workshop, Hunting for Disasters. This is the investigation phase. This is where engineers actively try to imagine every possible disaster before a single piece of hardware even gets built. And it all starts with a hazard identification, or HazID workshop. Basically, experts get in a room and are forced to think laterally using very specific guidewords. Words like no, more, less, or reverse. So you look at a function and ask, well, what if no part of the intended result is achieved? What if there's more of a pressure increase than we expected? It's a system that forces these experts to imagine exactly what could go wrong with every single function, user operation, and interface.
And this brilliantly illustrates what that looks like in the real world. Think about an underground station fire panel. A HazID workshop applies those guide words to every single connection. Someone pushes an actuator. Okay, what if the signal is not received? What if the system commands the fire dampers to close to starve a fire of oxygen, but the action is reversed and it opens instead? What if the automated public address system goes dead silent, or the ticket gates fail to open so people can't get out? By breaking the whole system down into these worst-case deviations, engineers can identify genuine, foreseeable hazards before they ever happen. Moving to step 3, calculating system risks, sizing up the danger. So identifying the hazards is really just step 1. We still have to figure out exactly how dangerous each of those hazards actually is. And we do this by breaking risk down into a pretty simple equation. It's the likelihood of an event occurring combined with the severity of the resulting harm. We categorize the likelihood from frequent all the way down to incredible, and severity from negligible all the way up to catastrophic, which obviously means multiple fatalities. Plotting each hazard across these metrics gives us a risk matrix. This is absolutely crucial because it allows engineers to strictly focus their design efforts on fixing the highest risks first, driving the overall danger down to an acceptable level. Step 4, the need for independence, the expert witnesses. But here's a thought. Who actually gets to say a risk has been lowered to an acceptable level? To truly prove safety, objectivity is absolutely non-negotiable. So the crucial point is that the people who design the system cannot be the only ones who say it's safe. You literally can't grade your own homework here. Standards for safety-related systems place a massive emphasis on independence. Roles like the verifier, the tester, and the safety assessor must remain entirely independent from the original designers. Why? To eliminate human nature. It ensures the assessor doesn't suffer from shared misconceptions, peer pressure, or those intense commercial pressures to just finish the project under budget. And our final step, building the safety case, the final verdict. This is the trial phase. It's where all those rigorous HazID investigations and independent testing run-throughs culminate into one undeniable verdict, the safety case. The formal definition is a documented body of evidence that provides a convincing and valid argument that a system is adequately safe for a given application in a given environment. And notice the word case here. It's used with the exact same meaning as in a court of law. It is the undeniable evidence offered up by the developer to back their claim of safety to the regulators. Now, what's really interesting about this is the history. Safety cases weren't just invented out of thin air. They were actually pioneered by the nuclear power and offshore oil drilling industries. We're talking about environments where a single failure means catastrophic, widespread disaster. The sheer complexity of these massive facilities meant that external regulators couldn't possibly investigate the systems deeply enough on their own to know if they were safe. Only the developers had the deep knowledge of the intricate engineering. So they flipped the script. The burden of proof was flipped onto the developers, requiring them to document and prove their own system's safety.
Let's see how this actually builds up, because physically, a safety case is not just a single piece of paper, it's a massive cascading library of shared evidence. It builds systematically. It starts with a super clear definition of the system. Then, it layers in the quality management report, which proves the work was done to high standards. Next up is the safety management report, proving the right processes were followed every step of the way. And finally, it dives deep into the technical safety report, which contains all those risk matrices and independent test results we talked about. It takes all this structured, layered information to finally formulate that valid, undeniable argument that a system is in fact safe.
So let's bring this all together. Complex systems earn their certification of safety through a highly uncompromising methodology. We started with the relentless continuous evaluation of risk throughout the system's entire life cycle. We looked at how engineers proactively hunt for failure using systematic hazard workshops and those very specific guidewords. We learned exactly why strict independence between designers and assessors is a critical barrier against human error. And finally, we saw how all this evidence is compiled into the ultimate, documented valid argument, the safety case.
We usually only think about these concepts when we're looking at massive power plants or incredibly complex railway networks. But I want to leave you with this final thought. How do these exact same principles of safety assurance secretly protect you in the everyday technology you rely on? From the anti-lock brakes in your car to the elevators you take in your office building, there is an invisible, rigorous world of engineering tirelessly putting technology on trial, proving its innocence so you can go about your daily life without a second thought. Thanks for joining me on this explainer, and I'll catch you next time.